All right, so welcome back, everybody, to the fourth lecture of parallel computing, our parallel programming class. So today we continue our discussion in shared memory programming. Okay, so far we have talked about shared memory systems and how you can program them using pthreads library in C and standard C++ library or std-threads, which was introduced in 2011 in C++11. And finally, we covered some parts of OpenMP. So we focused on OpenMP and we continue our focus on OpenMP today. So OpenMP, as I mentioned last week, it's a directive-based kind of library, but it is not a library that you have function calls. So it's a directive way of parallelizing your code. It has a lot of directives. So we covered some of them last week and we cover more today. But there are many directives supported by OpenMP. So you should take a look at their documentation to see what they provide, like in detail, because it's kind of it's a comprehensive API. All right. And then we talked about this fork join parallelism. Usually when it comes to OpenMP programs or generally in shared memory programming using threads as well, you start with a master thread or main thread, and then you create other threads on the fly. So that's called fork and join parallelism because you fork threads at some point in your program and then you join them together and then you can fork them again. So using this approach, you can gradually parallelize your code depending on the requirements that you have. So we talked a little bit about that product and that's our actual lecture today. So as an example, let's see how we can parallelize the dot product implementation and how we can do that using pthreads and C++ threads and also finally OpenMP. So let's see what is that product. So this is the equation for dot product. So I assume you have two vectors, A and B, and then you can define the dot product between A and B as this equation. So basically you need to multiply each element of the first vector to the second vector, and finally you sum them up. So before starting to develop a parallel program for this dot product computation, it's always good to start with a serial program. So as I mentioned in the fork join slide. So you usually start with a serial program and then you try to parallelize it. And that's the pattern when you want to work with shared memory systems. So let's see if anyone has an idea to implement that product in a serialized fashion. So any ideas about that? How we can implement that product just without any threads, just simply? Anyone?
Just nested for loops.
Sorry?
You want it not to be parallel, so I think we just use nested for loops, maybe for I
Oh,
and J, or
can we implement
is
it
it
in
like?
only one for loop?
Uh, I think so. Yes.
Yeah, so it's quite simple. So you just need to loop over the variables that you have in A and B. So using the elements of these arrays, and then you have a global variable called dot that you just accumulate. So I assume we have just initialize dot with something, double dot like that equals 0. And then you just compute this multiplication and add it to this dot variable, right? Super clear. So how can we actually parallelize this program? So we have this for loop. So, and this is what we want to compute. So how can we parallelize this loop? How can we parallelize this program? So any ideas?
Each independent operation has its own thread, let's say, and we'll use mutex or semaphores or something to lock the memory where we
Yeah,
save our data.
yes, that's one option. Let me ask this question more specifically. So assume you have n elements in your vector, n can be like 1000, for example, and you only have 4 threads, 4 hardware threads. So how you divide the work between these 4 hardware threads if you have like 1000 elements in your array? Of course, you can use mutexes. That's okay. We will get to that. But I want to know if there are other ideas as well. But the problem is with this dot, right? Because it creates a dependency between iterations. So if we didn't have this dot, and if we only wanted to compute AI times BI, then everything was okay, right? But how can we handle that with 4 threads in this case? So let me try to draw something for you. So assume this is my array, right? It has n elements. Right? Starting from index 0 to n minus 1. And I have 4 threads for T. It stands for threads. So what can I do to divide this n operations for these 4 threads? How can I assign these 4 threads to work on this array? Because I know the size, so I can specify what exactly I want to do with my threads, right? So what do you think about that?
3 threads will do the multiplication, and 1 thread will assign to dot when it makes sure that calculations are done.
Yeah, but
in other
here,
threads.
yes, in this case, I'm just using 1 thread to perform this stat, right? So I'm probably wasting some resources. What if I can compute? What if I can divide the data? Let me try to draw. Let me. I mean, what if I divide the data into chunks, right? So I have 4 threads. So probably I can have n divided by 4 chunks, right? So if n is, I don't know, 100, then I can have 25 element for each thread, right? Is that correct? So probably I can divide this array into 4 chunks. 1, 2, 3, and 4, right? I can then assign this part to thread 1, this part to thread 2, this part to thread 3, and this one to thread 4. Okay? And then I can compute 4 dots in this case. Let me try to erase this part. So I don't need this part again. So if I do that, I can compute 1 dot here locally, another dot here, another dot here, another dot here, right? So I have some small dot products instead of the whole thing. It's called block dot product, right? And finally, to compute the result, I just need to sum them up together, right? Does it make sense? Is it clear for everybody? So please give me a feedback so I see that you understood. Okay, good. So let's see how we can implement this idea. So here we are manually controlling everything, the number of threads, how we can divide the work between threads, and other things. So let's see how we can do that using pthread library. So here we have two arrays. In this case, I use C++ vectors, A and B, right? And then I defined an array called partial sum and with number of threads elements. So if I have 4 threads, then this array has 4 elements. Why I define that? To store these local dots, right? Local dot product results. Okay, so that's why I have as number of threads elements. Okay, so then I define a function here to perform that local dot product computation, and for that I need to have a starting point here for each thread and the end point here for each thread, which is easy to compute. So the first thing that I need to have is the thread ID starting from 0 or thread index. I can define that and I consider it as an input argument. Then I need to compute the chunk size for my data, which is n divided by the number of threads. And then for each thread, I need to define the starting point and the end point. The starting point is easy. So you need to multiply the thread index into the chunk size. And for the end part, depending if you can perfectly divide the n into number of threads, we can compute it like this. So if everything is perfect, it would be the start plus the start position, the start index plus the chunk size. Otherwise, you go until the end of the array, right? And then you define this local sum variable. You compute the dot product from the start to the end of that thread. So not the whole array, for that chunk that we considered. And then we store it in this partial sum. And this partial sum is a global variable, right? Because it is not defined in the scope of this function. So it's a global variable. Now I have a question for you. Do I get the race condition in this line of code when I update the partial sum or not? Should I use mutexes here as well? Should I use mutex here or not? What do you think?
No, you won't.
Yes, that's correct, because each thread is only updating its corresponding element in the array, right? So I don't get a race condition, right? So here I just updated the partial sum, which is the partial of this dot product. All right, so let's see how we can call this program. So the first thing that I need to do, this is my main function that I execute. So what you need to do first is to create an array of threads. So here we consider like this number of threads, probably 4, depending on your hardware threads. And then I created this array to store the IDs of threads. And then I created the threads, right? So here I have a pthread create for the ith thread with null pointer here. And then I assign this dot product function, which I defined here. And here I just pass in the address of the thread ID, right? Starting from 0. And then I call this thread join. So after this step, all the threads computed their partial sum and updated this partial sum array. Now the main thread here can compute the actual result, right? So we just need to sum over this partial sum. Okay, so here we start with the main thread, right? At this point, we fork some threads, right? They executed their own jobs, and then after this join is called, they join, and then the main thread here, and then the main thread here computes the result, right? So that's how we can manually create threads and coordinate them to solve this dot product problem. So now I have a question for you. Is it a data parallel work or task parallelism? So what we did, is it a data parallelism or task parallelism?
Data parallelism.
Yes, that's correct, because we are basically performing the same operation, but on different data. And we divided the data in this dot product worker function. All right, so I hope it's clear. So that was with P threads, and we can do the same thing with standard threads in C++. So the implementation here is a little bit simpler. So we can directly pass in this thread ID. Then we can divide the work like that. And here we just need to create threads, right? And then we call join, and finally we compute the partial sum. Okay, so that's basically the same thing, but with different syntax. All right, so let's talk about another example, which is quite important, and we have different implementation for that. So it's a numerical integration to compute the number pi here. So mathematically, we know that you can compute pi by computing this integral. So it's this integral in interval of 0 and 1. And this is the function that we need to compute the integral over. So basically, this is our curve that this function has, right? And we just need to compute the area under this curve between 0 and 1, right? And to do that, we can use this rectangular approach. So we divide the area under this curve into different, into different rectangles, and then we can compute the area of each rectangle, right? And then we sum them up, right? So this is an approximate solution for computing this integral. So this is exactly how we can do that. So we need first to create this delta x, which is this length, right? And then to compute the area of these rectangles, we just need to multiply this delta x by the height of this rectangle. And the height is computed by computing the value of this curve, right, in this middle point here. So that's why we have fxi times delta x. Here, delta x is the width of our rectangle, and the height of f of x can be computed by just computing this xi, and xi is the middle point of each rectangle, right? All right. So the first question here is how we can compute this integral with a serial program. Do you have any ideas how to compute that? Any ideas?
Very similar to the previous problem.
Yeah. So what should we do?
We'll see how many calculation in the summation, and we'll divide them into threads.
Yeah, well, I'm talking about the serial program, not a multi-threaded program, just a normal one. So what I can do is to compute this sum using a for loop, right? and then multiply the result of this sum to this delta x. I just need to calculate the value of xi, right? And then this f. So let's see how a serial program look like. So what I need to do is to first define the number of steps. So the number of these rectangles. Then I compute the step size, this delta x, right? Then I initialize the sum variable for computing this summation, right? And now I just need to compute it. So I loop over my my steps. I calculate x, which is in the middle, right? Using the step and the index that I have. And then I compute this function given the x that I calculated. And then I accumulate the sum variable. So after this for loop finished, I have the result of this part. And then to compute pi, I just need to multiply sum to the step length. And that's it. Then I can get pi. So I wrote the full program and I will send it after the class by Moodle. So is that clear for everybody? So this is important. And I think everybody should know how it works because we're going to parallelize this code step by step. So is it clear for everybody? Okay, what about others? Okay, take a moment just to understand. It's quite simple. So this is the main computation part. We compute xi, then we compute f of xi. In a loop, we sum them up and finally times it to this delta x. Okay. Well, let's see how we can parallelize it. But before that, let's see how we can measure the execution time of this program. So for measuring the execution time, in this case, we want to measure the wall clock time. You can use OpenMP as well, but here we are not parallelizing anything. We just use OpenMP to get wall clock time. So you just need to include OpenMP, right? And then we are interested in the time spent of this part, the main calculation, right? So you can define a start time using OpenMP get W time, which gets the wall clock time. And then you can get the end using the same function. And then here you can compute the elapsed time. So this is how you can measure the execution time of this program. But it's important to know what kind of time we want to measure. So essentially, for parallel programs, we can calculate wall clock time and CPU time. So anyone knows the difference between wall clock time and CPU time in time measurement of programs. What is wall clock time and what is CPU time?
I think the CPU time has more precision.
Okay, and?
It's like based on the frequency of the clock of the CPU?
Well, the CPU time and wall clock time, they have subtle differences. So let me see. So this is the definition of wall clock time. So when you use wall clock time, you consider the time that you spend for all kind of delays and IOs, right? But when you use CPU time, you exclude the idle time and IO waits. So you only consider the actual calculation, but using wall clock time, you also consider the IO and other kind of delays. Okay, so this is the main difference. But the more important question here that I would like somebody to tell me is that which one, in the context of parallel computing, we are more interested in. are we interested in wall clock time or in CPU time for parallel applications?
I think it will be wall clock time.
So do you know the reason?
Because if something went wrong, we need to know the time, including the delays and waiting.
Yes, but probably a bit more specifically, in parallel computing, we know that we need to send data back and forth, right? So threads are communicating through the data, through shared memory. And also in distributed memory programs, you have to explicitly send the data between the threads. So it is important to know the computational time, right? Like we have in this loop, but it is also important to know how much time we are spending for sending the data and for our communications. And this is something that is usually done, especially in distributed programming paradigm, using I/O and, for example, in networks. So we want to know the delays that causes us program using some I/O and sending some data as well. So that's why in parallel computing, usually wall clock time is more important than CPU time, right? So in your assignments, for example, or in your project, if you want to report the execution time, you have to report this wall clock time, not CPU time. All right? But this is just something that you should know. All right. So now we have a serial program, right? And we could measure its execution time or wall clock time. So let's see how we can parallelize this code. But before that, we have an important discussion on the role of memory in shared memory systems. So because it's quite important and it affects the overall performance of your algorithm. So the first thing that I would like to talk about memory is latency vs bandwidth versus bandwidth. So in a traditional uniprocessor system, you have a processor and then you have a memory. So it's the von Neumann, like traditional computer model, right? So basically, you know that CPU or processor needs some data from memory, so it requests data from memory, and then it wants to write some data into the memory. So you have memory access. In this case, you have load and a store, right? But when it comes to memory access, you usually have two costs. The first one is latency, and the second one is the bandwidth. So the latency is the time that it takes to send the data to the memory or to receive the data from the memory. So data is starting from the source until it reaches the destination. And it can be defined in different contexts as well, not necessarily between the CPU and memory, but also like networking, communication, and things like that. And the bandwidth is the rate at which the destination receives this data, right? Usually it is byte per second or gigabyte per second, things like that. So when you want to get data from memory to CPU or sending data from CPU to memory, these two factors are very important to know how much time you need to send the data or receive the data, right? So assume L is our latency and B is our bandwidth. So how can we compute the time, the amount of time that it needs to transmit n bytes in the system, right? So let's compute this time delay between CPU and memory. So we have the latency L, and we have n bytes, and we know that we can send b bytes per second, right? So the overall cost will be L plus n divided by the bandwidth. So we have a bottleneck between the CPU and memory in case of data access, because CPU is quite fast and memory is quite slow, and it takes like a lot of CPU cycles to get the data from memory or to write some data into memory. So we have this delay that is quite important in numerical applications because you need to fetch a lot of data from memory and you want to compute and then you want to write a lot of data into memory. So it's important to somewhat handle this bottleneck. All right, so there are efficient solutions for that. So what is the most popular one to improve the memory latency in terms of hardware design? Can anyone tell me? How can we reduce this latency between memory and CPU? It is one of the most important ideas in computer architecture. So anyone?
Optimizing the throughput and write and reading.
Well, so this is one solution, but what's the most popular one?
Memory hierarchy.
Yes, exactly. So we need to use memory hierarchy, or in the simplest case, we can use caches, right? CPU caches. So let's see how it works. It should be kind of familiar for you. So between the memory and the CPU or the processor, we put a fast memory called cache, right? Which basically is a collection of memory location that a CPU can access more quickly than it can access the main memory. But it is smaller than the main memory, however, it's faster, right? So it can improve memory latency because CPU needs to get data from the cache memory, which is faster than the main memory, right? So it doesn't, if the data is available in the cache, so the CPU does not need to get it from the main memory, and it can improve the latency, right? It's also important to note that these caches are managed by the hardware, so it's hidden from the software and also the developers, but it's important to be aware of it because it's important to write cache-aware programs to improve the performance. We will get to that just a little bit. So there are two terminologies when you use caches: cache hit and cache miss. So basically, if the data is in the cache and you can fetch it successfully, so you have cache hit. But if the data is not in the cache and you have to get it from the main memory, it means that you have cache miss, right? So being aware of these caches and the memory hierarchy is quite important in high performance computing. All right. So the next question is, which data should be stored in the cache? So what would be our policy to store data in the cache? So before that, I can show you a simple program, which is a sum program. So we have an array of 1,000 elements, or 1,000 floats, and then we have a for loop to compute the sum, right? So quite simple program. So we know that the arrays are like the arrays are allocated as blocks of contiguous memory locations, right? So in this case, if I can draw the array, so this is Z1, this is Z2, this is Z3, Z0, Z1, and Z2, and then Z2, and so on, right? So they are one after the other. So we know that if we read Zi, immediately we need to read Zi plus 1. So with a high probability, our program needs to access data in a predictable manner. So especially when you're working with arrays, we know that if you read Z0, then you need to have Z1 with a high probability, right? So this concept is called locality. Basically, locality is the idea that our program access data in a predictable patterns. And you have two sort of locality: spatial locality and temporal locality. A spatial locality refers to this fact that accessing things nearby previous accesses. So it means that if you get Z1, for example, you are likely to get Z2, Z3, and nearby elements, right? And temporal locality is about reusability. It means if you get some data from the memory, you're going to use it in the future as well. So it is called temporal locality. So this spatial locality and temporal locality is quite important when you're working with cache memories. And the cache memories get benefit of this, the concept of locality. So to exploit it, the memory access, when you want to work with caches, operate on the blocks of data instead of the individual data item. So here, for example, instead of only fetching Z0, like assume Z0, instead of fetching Z0 to the cache memory, we fetch a block of data into the cache memory, right? And this block of data is called cache line, right? Usually in some systems, it's about 64 bytes. So instead of fetching data items one by one, you fetch a block of data items with this, like, for example, 64-byte cache lines. So in this example, when I read Z0, so the system read 16 floats equally 64 bytes. And then instead of only reading Z0, I'm reading Z0 up to Z15, 16 floats from memory into my cache. So this is a very important concept in low-level programming, because you have to be aware of these cache lines to make sure that you are optimizing your numerical performance. All right. So another concept in caches, like for uniprocessor systems, is cache inconsistency. So assume you have some data in your CPU cache, right? And the CPU writes something into your cache, which causes the value in the cache to be updated. So in this case, the value in the cache is different from the value in the main memory, right? So this is called cache inconsistency. Typically, we have a couple of ways to handle this inconsistency, but there are two main approaches, which I would like someone to tell me what are they. So what are the main methods to handle cache inconsistency in a typical computer system? Any ideas? All right. So those methods are write true and write back. With write true, you write to cache and the main memory at the same time. So whenever you want to change the data in your cache, you change the data in the memory at the same time. But with write back, if the data is changed in the cache, you mark that data as dirty. And when you want to replace that cache line with another cache line, you write that dirty cache into the main memory. So it's kind of delayed version of this write through. Okay. So these are general concepts that I wanted to convey about the caches. So the takeaways are caches are fast memory locations, and they are used to reduce the CPU memory bottleneck, right? And we have different level of caches, not only one, but I just wanted to make this simple enough to understand. And the data that is stored in the cache is using data. For storing the data in the cache, we use the principle of temporal and spatial locality, which are important concepts. And then it's also quite important to know that the data between memory and caches are transferred in cache line, not individual data items. And finally, in high-performance computing, it's quite important to write cache-aware programs. And you will do it in your second homework assignment, when you want to improve this matrix multiplication that you had in the first assignment using a cache-aware cache optimization method. All right, so this was about caches in uniprocessor systems. So now let's see what happens with caching when we have shared memory systems or multi-core systems. So in multi-core systems as well as single-core systems, we use caches to improve memory's performance. So for example, in this case, we have two processors, right? P1 and P2, and each one has its own caches, right? So we have L1, L2, and 3 cache levels, but usually L1 cache and L2 cache are private to each processor. And in this case, we consider the caches to be private. So cache 1 and cache 2 are private to processor 1 and processor 2, respectively. And finally, we have a bus that connects each processor, the processors, to the main memory. So this is a very simple architecture for a multi-core system, right? All right. So as I mentioned, each processor has its own cache or multiple caches, depends on the architecture. And then they have the same strategies. However, here in the multi-core system, we might have longer latencies because we have more processors. But there is a quite well-known problem when you use caching in multi-core systems, and that problem is called cache coherence problem, which again, as a programmer, you should be aware of this problem. So let's see what this cache coherence problem is. Okay, so in the same system with two processors and a global memory and two caches, assume we have a shared variable x, which is stored in the global memory, and the value of x is 2. And in our CPU registers, which are private, small private memories in the CPU chip, we have y1 variable in the first processor, and we have y2 and z2 variables on the private memory of the second processor. Okay? Assume at the time step 0, these are the computations that are done by the first core and the second core, P1 and P2. Assume in the first time step, we want to assign y1 to x, and we want to compute it in the first core, and we want to assign y2 equals 3 times x in the core 2. What is done is the following. So we first put this data, like fetch this data from the memory into cache of the first processor, right? And then we do the assignment. So here y1 is 2, right? It comes from the memory to the cache, and then from the cache to the CPU register. And then we do the assignment here, right? And we do the same thing for the second core. So we fetch data from the memory to the cache of the second processor, and then we do the assignment. So here y2 is 6. Quite simple. In the next time step, we want to change x to 7. And this is done by the first processor. And the second processor, in this case, does not do anything related to x. So here what we do, the first processor wants to get first needs to get this x, because x is already available in the cache. So it is a cache hit. So, and then it can change the value of x from 2 to 7, right? But x is in the cache. So the value of x is changed in the cache, not in the main memory, right? And also not in the cache of the second process. In the next step, the first processor does not do anything related to x, but the second processor wants to update this z2 variable with this 4 times x. Okay, so someone tells me, this is a question for you, what would be the value of z2 in this case here? What z2 will get after this instruction executed? Is it going to be 28 or it's going to be 8?
I think 8 because it's not updated.
Sorry?
It should be 8 because it's not updated in the second cache.
Yes. So it's going to be 8. Why? Because the second processor gets its data from the cache because the data is available in the cache. Okay? So it's 8. But the answer should be 28, right? Because we updated X here and we want to have X updated everywhere. So why why Z2 is not 28? Anyone knows that? It's quite simple.
The value of the 7 was not moved from the first to the second cache memory.
Yes, that's true. That's mainly because the value of X in this cache is different than this cache, right? So we have differences in two caches. So because we didn't synchronize them, right? So this problem that you have different values in different caches for the same global data is called cache coherence problem. So now another question. What if I use this write true or write back cache policy? Can I remove this cache coherence using this write true? In the write true policy, we update the cache and the memory at the same time, right? So does it solve this cache coherence problem or not?
No, because it is still a cache hit and it doesn't get the new value.
Exactly. So because X equals 2 is still in the cache of the second processor, although we updated that in the memory, but it is not updated in the second cache, right? So this is the cache coherence problem. And formally, in multi-core systems, inconsistencies arise when multiple caches hold the copies of the same shared memory location. So if you have the global variable in the memory, but you have different variable with different values for the same variable in the caches, so then you have this cache coherence problem because you didn't synchronize them, right? So there are some approaches to solve this cache coherence problem, and they are mostly implemented in the hardware. One of the most famous ones is a snooping cache coherence protocol. And another one is a directory-based one, which is usually used in distributed systems, but I'm just explaining this snooping cache coherence one. So let's see what it does. So as you can see here, we have a memory bus. We have a bus that connects all the processors, right? So if I update my cache data in this processor, I can send an information through this bus, and that information can be seen by the other processors, right? So for example, when P1 updates X in its cache, it can broadcast the update information, which in this case about the cache line containing X, because we are operating on cache lines, across the bus. And then the second processor or other processors, they should snooping the bus. They should investigate the changes using the bus. And then when they know that the cache line containing X has been changed, then they invalidate the value of that variable in the memory in the cache. And then if they want to fetch that data, because it is invalidated in the cache, they have to fetch it from the main memory. So if the first processor used this write true or write back policy, then it updates its cache variable and the memory variable. And here we have invalidated that data. And then P2 needs to get data directly from memory that is already updated. So this is a Snoopy cache coherence protocol or cache coherence protocol that is implemented in the hardware to avoid this cache coherence problem in multi-core systems. Okay? All right. With cache coherence protocol, another problem comes into play, which is called false sharing. And again, it's important to avoid false sharing in your code. So to explain that, first you need to remember that the caches, especially CPU caches, operate on the cache lines, not individual variables. So this is the main source of this this false sharing problem, right? So assume here we have this code, and in this code we have a nested for loop, so 2 loops we have here, and we want to compute this value, right? And f is an arbitrary function. And we want to divide this code into like between two P cores or P processors. And for doing that, we can assign the outer loop iteration, this one, to P cores. So basically, if we have M data that we want to work on, we can divide M by P, then we can divide it between P processors, right? So in this case, assume we have, for this example, assume we have M data points that we want to work with, and we have 2 threads or 2 processors, and the cache line size is 64 bytes. Okay, and here is the code that we developed. So this part of the code is done on one processor, and this code snippet is performed on another core. And you can see here how we divide that. Okay. So let's see how this false sharing problem happens. So we have our code, and this is assumed to be our hardware. So we have 2 cores here, core 1 and core 2. We have 2 threads, thread 1 and thread 2. Each core has a private cache, right? And here is our cache, and here is the memory. And we considered M here to be 8, right? So if we have M doubles, right? So Y is an array of 8 doubles, right? So in this case, how much memory does this array Y will consume? Right? We have 8 doubles, right? What is the size of each double in byte?
8.
So 8 bytes, which means we have 64 bytes, right? And this is important because our cache line size here is also 64 bytes, which means this array, which lives in the memory, completely fits our cache line, right? So let's see what happens. So we want to do this computation by the first core and this computation by the second core, right? So let's see what it does. And this array ym is in our global memory. So in the first core, we need to get y0, right? Because here we are just accumulating to y0. So we need to read y0. When thread 1 wants to read y0, it means that the data should be in the cache. Because it's not in the cache, so we send the data to the cache, and this is done by hardware. And because it is done in cache lines, and the whole data fits the cache line, so it sends the whole data into the cache. So now we have the whole array of y, right, in the cache. So far, so good. And then the second thread wants to work with this element in the array. And because the whole array fits into the cache line, this element also is in the same cache line. So which means the entire array Y is one cache line. It doesn't matter which core is fetching it from the memory. This array lives in one cache line, so you don't have two different cache lines, right? And this is something done by the hardware. So we have the same data here in the cache of the second core, right? Because they live in the same cache line. All right. So far, so good. So far, nothing very difficult and problematic happens. But the problem starts when thread 1, for example, wants to write into Y0, because this is Y0, right? When it wants to write to Y0, it means it changes the value of this array in the cache, right? So the local cache is updated. So when the local cache in a multi-core system is updated, the cache coherence protocol is activated, right? And because the cache coherence protocol is activated, so it sends this information through the bus to all other cores, and it causes the second core to invalidate this data that was in the cache, right? And because the data is invalidated, when the second thread or second core wants to work with this data, because it is invalidated, it should fetch the whole data from the memory again, right? So here we are losing some performance because instead of using the data which is available in the cache, we are using, we need to fetch the whole data again from the memory. And after this step, thread 2 wants to update the data in the cache. And then, because of the cache coherence protocol, the data in the first cache is going to be invalidated. And then the first thread needs to get the whole data from the memory. So in this case, we are just fetching data from the main memory, and it means that our cache is not working. And in this case, we lose a lot of performance. So that's called false sharing problem. And it is called false sharing because the system is behaving as if the elements of Y were being shared by cores, but it's not like that. And it is important to note that false sharing does not cause incorrect results because the results are going to be correct because of the cache coherence protocol, but it ruins the performance. So you lose your performance. To handle this situation, to handle this false sharing problem, one method is to make sure that the data that is shared between threads live in different cache lines. So if we are make sure that the data is not on the same cache line and each CPU cache has a different cache line, right? Then in this case, we are not going to get this false sharing problem. And to do that, we can use something called padding, which roughly means you can insert extra unused bytes between the elements, right? So if you have an array like with 8 bytes, you just fill in between with some unused bytes, right? To exceed the cache line size, then you will get different cache lines. So yes, so these were the concepts about the memory in multi-core systems. And now when we want to parallelize this Pi program, you see that how we can avoid this like false sharing that's caused by cache coherence protocol. All right, any questions so far? And this code is for you to study as an exercise. So this is one way of implementing this padding. But you'll see another version. All right. So let's see how we can parallelize our Pi program. So we use we do it with OpenMP, but in a manual way, and then we try to improve the implementation step by step. So this is the code for parallelizing this Pi program using OpenMP. So similar to what we did with dot product, we create an array. Let me erase it. So we create an array called sum to compute the partial sums, right? Similar to what we had for the dot product, which contains as many elements as the number of threads that you have available on your system, right? And then we have this pi, like initialize, and then we set the number of threads, and then we want to get the wall clock time. So easy so far. Then we have to specify that, hey, OpenMP, we want to have a parallel region, right? We want to fork some threads. And we can do it using this pragma OMP parallel within this block. So anything that runs in this block runs in parallel, right? Because OpenMP creates threads, creates a team of threads with this num-thread number, likely, and then each thread will execute this block independently. Okay. So what I do is the following: I first get the thread ID, similar to what I did in the dot product, and then I get the number of threads in this parallel region. Then we update the number of threads if it was necessary, and finally we implement this for loop. So here we had a slightly different strategy for parallelization. If you remember, in the dot product, we divided data into chunks. First chunk with thread 1, second chunk with thread 2. But here we did somewhat different. If you read the code, you will realize that if this is our array, right? What we do is we assign thread 1 for this element, so T1, thread 2 for this element, thread 3 for this element, and thread 4 for this element. And then here we have thread 1 again. And you can implement it using this for, right? So we start from the thread ID, right? And then until the number of steps, and then we increment I by the number of threads. So we jump from here to here for the thread 1, or here to here for the thread 2. If you take a look at the code, you will understand this strategy. Okay. So, and finally, I just partially update this sum array for each thread, right? And then I loop over this partial sum here, and then I compute pi. All right. So here is a benchmark with 100 million steps, like this, number of steps for the integral. And the results are somewhat interesting. So if I use one thread, I will spend about 2 seconds. But if I use 2 threads, I spend 2 seconds, roughly. But as I increase the number of threads, like after this 4, like to 8 and 12, you see that instead of reducing the time that I used for my computation, I'm actually increasing the execution time. What I expect is that if I reduce the number of, if I increase the number of threads, I should get less time, right? I should get less execution time. So what is happening here? So why do you think my performance is not so good as I have more threads?
When we have number that's bigger than the actual CPU cores or threads in the hardware.
Actually, no. I use the exact number of threads that my hardware had available. So look at, Yes.
Because the number of sums that we have to do is going to increase.
Well, you picked the right array, but take a look at what we saw today. Yeah, the problem comes with this sum here. So does it sound familiar to what we saw today? Because we have different threads, right? Updating this sum. So we have a sum array, right? And we have different threads working on the elements of this sum. And the sum is a short array, so it's not a long array. Is it similar to false sharing problem or not? Is it? Well, if you look carefully, you see that false sharing is happening here because the sum array is very small compared to like the number of threads that I have. And in my system, I have 128 bytes for the cache line. And as I increase the number of threads, I am fetching more and more from the memory, and it provides a bottleneck. So it's a false sharing problem hidden in this problem. It is quite hard to detect false sharing in practice, but this is a very common pattern. So when you like define an array like this, where each thread needs to write into this array, so it should be somewhat familiar for you because it can cause a false sharing problem. So try to avoid this kind of pattern as much as possible. So let's see how we can improve it. So one method to solve this false sharing problem was padding, right? So here I define a pad size to be 16. To be 16 because my cache line is 128 bytes. So 16 for doubles, right? 128. And then in this partial sum array, I create a 2D array, right? With the number of threads, and also the pad size, which means because if you know in C, we are storing data in a row major. So if we have, for example, 2 threads, and then we have this pad size, so this would be the first row, so the first thread, right? But here we have about 128 bytes that are unused, right? And then we have the data for the second thread, right? And another 128 bytes, right? In the previous implementation, if you consider 2 threads, the implementation was like that. Yeah, an array of 2 threads. But now we have an array of 2 threads as well, but we pad the data by 128 bytes. So this is how this multi-dimensional array implementation looks like in the memory, like that. And then we do our computation like before, but here we update only the first element, like here and here, instead of the whole thing, okay? So it causes this to happen, that this part will be on one cache line, and this part will be on another cache line. All right. So now look at the results. If I have one thread, I spend 2 seconds. If I have 2 threads, I spend 1.1. So I have nearly 2 times the speed up as I expected. If I use 4 threads, then it becomes to 0.5, 8 thread 0.4, 12 thread 0.3, right? And in the next lecture, you will understand why we have this behavior in a speed up. So as we add more threads or more cores, so this is P, and this is the speed up, you see that we reach a saturation point, which is called Amdahl's law, which we talk about in the next lecture. But the good thing that we can see is that by avoiding false sharing, we can have a huge improvement in the performance, right? In the previous slide, you see that for 12 threads, we have spent 3 seconds, but now we have spent 0.3 seconds. So it's a quite good speed up in the performance. All right, so this is how we can avoid false sharing in this numerical integration problem. All right. So let's see some other functionalities that OpenMP provides, and they can also be used to avoid false sharing, but without padding, for example. So it's more convenient way to write high-performance programs. So OpenMP provides different synchronizations, like critical or barrier, and also many more. But today, we just talk about the critical and barrier. For others, you should take a look at the documentation. So let's see what this critical and barrier do. So basically, what they do is to impose some order constraint on the a thread execution to protect the shared data or to avoid this race condition. So let's see what they do. So the first synchronization method is the critical one. And this is how you can define it, like here. So it basically means if you have multiple threads here, right? Only one of them can get into this critical section, right? So it is similar to the mutex lock. So if you have 3 threads, one of the threads will get into this block, and the others need to wait. And as soon as this thread leaves this block, another one can come in, and then the third one will be waiting. So this is the critical synchronization that you can use to avoid data race. So for example, here we just protected this rest variable using this critical section, and make sure that these pragma OMP critical is within this pragma OMP parallel. So you must have this pragma OMP parallel, and then other OpenMP directives can be used inside. Otherwise, it doesn't do anything. So the next synchronization method that we're going to talk about is barrier. Basically, using barrier, we define a point in the program that all threads must reach before any thread are allowed to proceed. So it's a waiting point. So for example, in this part, again, we should use it within this pragma OMP parallel directive, right? So if we define pragma OMP barrier, all the threads that are created here will wait here, right, at the barrier, and after all of them reach this point, then they can execute this block. Okay, so this, and keep in mind that barrier is kind of expensive synchronization, because all of the threads need to be idle until the others can do the other job, right? So because they have to wait here. All right, so let's see how we can avoid false sharing that we had in the previous problem using this synchronization, using this critical synchronization, right? So what we can do is the following. So we don't use that array for computing the sum, the partial sum. So we completely remove that part. So we don't use an array even with the pad version. So we just define a double for the sum. And then in each thread, we do exactly what we did before, but we just accumulate to the sum, similar to what we had in the serial program. And then when we want to compute pi, we just protect it using this critical directive in OpenMP, right? So now I have a question for you. It's a little bit tricky, but am I getting a race condition here or not? Should I use like this critical to protect this sum variable, or that's fine? What do you think? Any ideas? Here, when I compute pi, I might get into race condition because pi is global. So it's not defined in the scope of this local threads. It was defined here, like pi equals 0. So it's a global variable, and all threads have access to that global variable. So that's why I need to protect it using this critical. But what about the sum? You can see that sum is declared and defined here within this OMP parallel section, right? And every variable that you define in this OMP parallel section is considered to be private. So it means no other threads have access to this sum variable. So in this case, you don't get this race condition because it's a private variable, right? Similar to what we had in the first example in dot product. But here you have to use this critical for protecting that because pi is a global variable. All right. Okay, so in this case, we didn't have that partial sum array, right? So since we didn't use any array for storing the results, the partial results, so there's no false sharing. So another method that you can avoid false sharing is using this critical directive in OpenMP. Okay. So let's talk a little bit about loop parallelization. That is quite simple. So assume we have a for loop with independent steps. So you can easily parallelize it using OpenMP, using this pragma OMP4. And this should be defined within this pragma OMP parallel. So in this case, OpenMP split up split up the for loop automatically based on the number of threads that you have available on your system. And here, after the for loop is done, like at this point, you have an implicit barrier to make sure that all threads did the computation in the for loop before executing the other parts of your program. Okay, but you can avoid this barrier as well using a directive called no-wait, which is not the topic of our lecture. Okay, so this is how you can automatically parallelize for loops using OpenMP. So basically, you have different ways to do that. So let's see how they work. So assume we have this sequential code. We just compute a vector addition, right? So it's a serial code. We can use this pragma OMP parallel without parallelizing for loop, and we can do it completely manually, as you saw before. So you just have to define the number of chunks, like the starting point, the end point, and then you can control the for loop manually, right? So this is called the manual parallelization or manual for loop parallelization, which you can do, but OpenMP makes it automatic for you. So if you use multi-threaded programming using pthread and like C++ threading library, you should use this manual thread assignment. But because OpenMP was kind of designed for parallelizing for loops, so it can do this thing automatically for you behind the scenes. But you need to use pragma OMP parallel and pragma OMP4 together. Not necessarily together like that, but pragma OMP4 should be contained by this pragma OMP parallel, right? And this is a shortcut actually, so I don't know why I didn't bring it here. Yes, so you can have this pragma OMP parallel and pragma OMP 4, and then you specify your for loop. Make sure that this is, in this case, should be here, and you don't have this 4. Oh, sorry. So this is okay. So just let me fix it. So there's a typo here. I will fix it in the final version. But basically, when you have this pragma OMP parallel, so it should be like that. You don't have this 4, but this directive should be inside, like after that. So you have pragma OMP parallel, and exactly before the for loop, you should put it this pragma OMP 4. But there is a short way of doing this, which is called pragma OMP parallel 4, which is the combination of these two together. So using this pragma OMP parallel 4, you can actually parallelize this code automatically using OpenMP. All right. And you can do it for nested for loops as well. So for example, here we have 3 for loops for doing matrix multiplication. But here we want to parallelize 2 outer loops. So then you can use this collapse followed by these 2, which means collapse these 2 for loops into 1 loop and then apply this OMP parallel 4. So it depends how many for loops you can basically parallelize on your program if you don't have dependencies. All right, so collapse is used for nested loops. All right. So the next operation, which is quite important, and we studied a lot, is the reduction operation. And the reduction operation refers to the operation that combines values from different threads into a single accumulation variable, like this one. Right? So here, for example, we want to compute the average. So we have an array, and we want to compute the average in this array. So we have an operation plus, in this case, and then we sum all of the elements, and finally we compute the average. So this part is called a reduction, because we are combining values of I into one variable. And for a reduction, we need a variable that you want to reduce the operation to, and an operation like plus, multiplication, minus, maximum, minimum, things like that. And the reduction is also implemented in OpenMP. And when you have it, you should use this reduction directive, where OP is the operation that you want to use for the reduction, and list is the list of variables that you want to perform reduction to. So for example, to compute the average using reduction, we initialize the average variable in the global space, and then we put it here in the reduction clause, and then we want to have this plus operation, right? And then OpenMP automatically parallelize this reduction for you. And it is doing that by, having a local copy of this variable, like average here, and then it updates this local variable in this parallel region, and finally it sums them up together to have this average computed. So it's quite simple. I don't spend a lot of time in explaining these things because it's quite easy when you read that. So for example, in our dot product example, this is the serial code, right? And using the reduction, you can implement it in a parallel manner quite simply. If you compare it to the pthread or C++ thread implementation. So you use pragma OMP parallel 4. You want to parallelize this for loop, and then you have a reduction on this dot variable. And the reduction operation is this plus. You want to sum sum them, right? So you can see how easy is the dot product implementation in parallel using OpenMP. And we can use the same thing for our Pi program here. So here we have like this part is quite important. So we have this pragma OMP parallel 4, and we perform reduction using this sum on the sum variable, right? So we have the sum variable here, which we want to perform reduction, and then we compute pi. So this is one of the most optimal programs that we could write for this pi computation. So here we don't have this false sharing. We don't need to control the loop ourselves. We don't need to control the starting point and the ending point of the threads ourselves. So everything is done automatic. You just need to perform this pragma OMP parallel reduction. This pragma, you just need to use this. And I implemented all of them, so I will get you the code. And as an exercise, I think you should like benchmark these different parallel OMP implementation, the one that we did manually, the one with padding, the one with critical, and the one with this reduction, and just compare the execution time on the execution time of these different algorithms. And probably you can come up with some sort of graph or a table to see how these improvements in parallelization and implementation can really affect the performance. All right, so there's only a small topic called task-based parallelism using OpenMP that I think I can create a separate video and post it on Moodle, or we can talk about it in the beginning of on the next class. But I think that's enough for today. So try to practice what you have learned and see how these OpenMP directives work. And I also recommend you to take a look at the documentation. By the way, there are some resources if you want to learn more about OpenMP. And for that, you can take a look at this GitHub repository that will be available. Like the address of this repository will be available in the slides. All right, so I think that's enough for today. And we are not going to discuss more lectures on OpenMP. So our next lecture will be dedicated to parallel program design and analysis, and we gradually talk about GPU computing and how you can write CUDA programs. All right, so if you have any questions, it's a good time to ask now.
Regarding the assignment, you mentioned groups.
Yes.
Like, is there a different criteria of what's required if someone do it individually versus in a group?
Yeah, you are free to do it individually or in a group. So it's not mandatory to be in a group. So that's okay if you do it individually.
Okay, so basically the same criteria.
Yes.
Okay, thanks.
All right. So have a good week and see you next time.